Welcome, ladies and gentlemen, to your MN34 notes, where we're going to talk about angle sums in polygons. This is section 8.1 in your textbook. The objective statement here states that we're going to find the sum of the measures of the interior angles of a convex n-gon. And let's recall that an n-gon is a polygon with n sides and n vertices. To make that a little bit more real, let's just, instead of saying n-gon, let's say a 14-gon. So we can put a number right in for n. And what that polygon means then, or implies, is that it has 14 sides and 14 vertices. So today we're going to first explore the sums of interior angle measures. And really what's going to happen is you're going to derive the formula for the polygon interior angle theorem. The instructions or the steps are in three parts, where the first one, it says draw polygons. Use a straight edge to draw convex polygons with 3 sides, 4 sides, 5 sides, and 6 sides. And what I did, just to make it a little bit more straightforward, is I have the pictures around your note guide for you. So step one is really taken care of. Step two, we're going to draw diagonals in each polygon. Draw all the diagonals from one vertex. A diagonal, of course, is a segment that joins two non-consecutive vertices. Notice that the diagonals divide the polygon into triangles. See the example to the right. Well, here's what we're going to do. We're going to actually start to the left because I put these shapes in here for you. And we're going to start with this quadrilateral. And I'm going to start at this vertex over there in the far left-hand corner, and I'm going to draw diagonals. Diagonals, again, go from one vertex to another vertex. And it can't be non-consecutive, or excuse me, consecutive, because otherwise it's actually the side of the shape. So I'm going to go from this vertex across to, and create a diagonal to the opposite vertex. And there's no other diagonals we can make here, or for cutting the shape up. So we're not going to any other vertex once we pick the one vertex. So let's go over to this pentagon, this five-sided shape. And again, I'm going to pick this vertex up here. You can pick any vertex, but once you pick one, just stick with it and draw the diagonals from that vertex. So again, you can't draw to this side, because otherwise it would actually be the side of the pentagon versus a diagonal. So I'm going to go right here and right here. And then again, do the same with this hexagon, a six-sided shape. So I'm going to start and draw my diagonals. So now, once we've done that, really what it's done is we've cut up these shapes into multiple triangles. So for instance, up here in the quadrilateral, we have one triangle, two triangles. In this pentagon over here on the right-hand side, we have one triangle, two triangle, three triangles. And this hexagon, we have one triangle, two triangles, three triangles, four triangles. And we know, because we've talked about triangles forever now, it seems, that when you add up your interior angles of a triangle, that, of course, equals 180 degrees. So notice step number 3. It says fill in the table. By the triangle sum theorem, which we've talked a lot about in our class, the sum of the measures of the interior angles of a triangle is 180 degrees. Use the theorem to complete the table. So now a triangle, if you look at down here with this table, the triangle has clearly three sides. And because a triangle is a triangle, it only has one triangle. And because triangles add up to 180 degrees, we can say there's one triangle times 180 degrees, which means the sum of the measures of the interior angles of a triangle is 180 degrees. This we know. I mean, this is something that we know, and I know that this seems kind of redundant, but the fact remains that we're kind of setting up a pattern here to see if we can derive this theorem, which is called the polygon interior angles theorem. Okay, so let's talk about a quadrilateral. A quadrilateral has how many sides? We've got 4. If you look up at the quadrilateral, when we cut it into using the diagonals, we broke it into 2 triangles. And then over here on the far right part of the column, we have 2 triangles. times 180 degrees, because each triangle is 180 degrees, is going to equal a total interior angle measure of 360. And if you know anything about quadrilaterals, when you add the four interior angles of a quadrilateral, that confirms what we've talked about in previous math classes, which is that the four angles in a quadrilateral add up to 360. Think about a square, a rectangle, and so on. The pentagon. The pentagon is a five-sided shape. And if you look over to the right here where the pentagon is, you notice that we have three triangles when we broke it up using our diagonals. And again, following this pattern, if we have three triangles, and each one of those triangles is 180 degrees, we can multiply 3 times 180, which is going to give us 540 degrees. Okay, so what we're saying is a pentagon will have 540 degrees inside if you add all those angles together. Again, the quadrilateral is 360, the triangle is 180 degrees. The hexagon's interior angles. So if, again, we're looking at these interior angles, the first thing we're talking about is the number of sides, which is 6. The number of triangles that was created is 4. And following the pattern and our logic, we know that if we have 4 triangles in there and they're each 180 degrees, that we are going to have 720 degrees total inside of that hexagon. Now, this is where we're looking at the table and trying to see the pattern, and we're going to generalize it to an n-gon, any sides, not just a 3-side, 4-side, 5-side, 6 sides, but any sides. So that's why we have an n right here, because that represents any number of sides. And notice what's happening from the number of sides to the number of triangles. You go from 3 to 1, then all of a sudden you're going from 4 to 2, you're going from 5 to 3, 6 to 4. If you look at the pattern, all you're doing is you're taking however many sides you have in the polygon, and you're taking away 2. So look at your pattern. 3 minus 2 is 1, 4 minus 2 is 2, 5 minus 2 is 3, 6 minus 2 is 4. Then from there, we take that second column, which up above was 1, 2, 3, 4, but now it's n minus 2 because that's our general idea. And we take that and multiply it by 180 degrees. And this, my fine ladies and gentlemen, is the actual polygon interior angle theorem. So rather than me just saying, hey, this is how you find how many angles are in, or excuse me, how many degrees are in any kind of polygon, I wanted you to really understand where it derives from. So here it says the expression of finding the sum of measures of the interior angles of a convex n-gon is, and we are going to rewrite it just so we have it, n minus 2 times 180 degrees. And if you want to read a little bit more about it, it is on page 507 in your textbook. But this is a star moment because we want to make sure that we don't forget where that formula is. That is a biggie. We're going to be using that a lot the rest of the school year and further. Okay, so let's make the connection here. Okay, so it says using the pattern from the table, find the interior angle measure of an octagon. Well, and maybe we should just kind of go right down here. An octagon has 8 sides, and most people are okay with that one. A decagon has 10 sides, and a 15gon, just like it states, has 15 sides. Now, some that you might, I'm just looking at it. We have triangle, quadrilateral, pentagon, hexagon. Hepta, by the way, is 7. So let me just put that in case you've forgotten heptagon. 8 is octagon. 9, we could either say a 9gon or a nonagon. Nonagon. And we've got the 10 sides. And then from there we say 11gon. Sometimes people will say the dodecagon for 12, 13, and so on. But really, if once you get past 10, if you say 11gon, 12gon, 13gon, we're all good. Even the 9, if you're forgetting what a nonagon's name is, just write 9gon. It's all good. The ones you do need to remember are obviously triangle, quadrilateral. You do need to know pentagon, hexagon. You do need to know heptagon, octagon, and then that decagon. But like I said, the nonagon seems to be one that students forget. Okay, so looking at this formula for finding the interior measure angle. So we're talking about if we want to know what the total angle measure inside any octagon is, it'd be using the pattern n minus 2 times 180 degrees. So since we know the number of sides is 8, we can put that right in. So 8 minus 2 times 180 degrees. And so 6 times 180 degrees is going to equal 1080 degrees. So if you add every single angle inside of that octagon, no matter what the octagon looks like, it's going to be 1080 degrees. Decagon, again, 10 sides. We can go 10 minus 2 times 180 degrees. And that's going to be obviously 8 times 180. And if you calculate that up, you get 1,440 degrees. And why don't you pause this video right now and do the 15 gon on your own and then restart once you have your answer to check with me. Voila, 2,340 degrees should be your answer. Now keep in mind again, when you're using your calculator, you do what's in the parentheses first, and then from there, in this case, it would be multiplication. So 15 minus 2 first, which is 13 times 180 degrees. So make sure you get your order of operations correct, otherwise it's going to be a problem. Okay, so that's finding the interior angle measures of any polygon or how you can find it. So if, for instance, you have a 100-sided figure and you want to know what the inside angle measures equal, you can put that into that polygon interior angle theorem and voila, you get your answer. Now the polygon exterior angle theorem is a little different. Well, not a little bit, it's a lot different. It says polygon exterior angle theorem, the sum of the measures of the exterior angles of a convex polygon, one angle at each vertex, is 360 degrees. Now make sure, again, you're really understanding the difference between interior angle measures and exterior angle measures. These right here, bam, 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 those are interior measures because they're inside the polygon. Exterior angles are the angles that if you extend the sides, like this one here, and let me just, actually before I do this, let me count how many sides this is. 1, 2, 3, 4, 5. So this is a pentagon. And all that you do to find the exterior angles is you just extend one of those sides a little bit, and this would be one of your exterior angles. And then you keep going. This would be another exterior angle, another exterior angle, another exterior angle, another exterior angle. And I think your picture is slightly different, but it's still the same idea. So if you see in this example, it says the measure of angle 1, 2, 3, 4, all the way up to 5 is equal to 360 degrees. Ladies and gents, this never changes. So the great thing about exterior angles is no matter what the shape is, if you extend those sides to create exterior angles and add those angles up, they will always give you 360 degrees. Interior angles change with the number of sides. Exterior angles never change. So it doesn't matter what shape it is, whether it's a hexagon, pentagon, 20-sided 20gon, it's still going to equal 360 degrees for exterior angles. Okay, so we have example, a convex hexagon. Hexagon, as we know, is 6 sides. Has exterior angle measures with 3, 49, 58, 67, and 75. What's the measure of that 6th vertex? So, you can draw it, for sure, you can draw it. Or in this case, I'm just going to say, we know one of the angles is 34 degrees. We know the next one's 49. We know the next one's 58. We know the next one's 67. We know the next one is 75. So this is 1, 2, 3, 4, 5 sides of a hexagon. The third or the 6th side we don't know, so we're just going to put whichever variable you want. A for angle, X because we use it all the time, whatever. When you add all these together, whether it's a hexagon, pentagon, whatever, it's going to be 360 degrees. And then you know what? You solve it from there. And this is just a linear algebra problem, very nice and straightforward. We want to add 34, 49, 58, 67, 75. Okay, so when we add those angles together, we get 283 degrees. All of this right here gives me 283 degrees plus x equals 360. We take that 360 and subtract that 283 from both sides. Let's see, so 283 minus 283. So we have x is equal to 77 degrees. So that last angle in that hexagon is 77 degrees. So just to recap, if you're talking about interior angles, the formula that you're going to use is called first of all, the Polygon interior angle theorem, and it's that n minus 2 times 180. So the n fluctuates depending on how many sided polygon you have. The exterior angle theorem is literally adding up your total angles, and that will give you 360 degrees. Thank you for joining me.